Geothermal systems experience seismicity as part of their natural function. When humans intervene in these systems to harvest power from them or seek to create engineered subsurface reservoirs, like in EGS, small man-made earthquakes, called induced seismicity, are relatively common and typically go unnoticed by humans. But there have been instances, though, where geothermal energy projects, either during their operation or while being constructed, have been directly linked to more significant earthquakes. So, what do we know about how and when these seismicity events happen? What technologies and methodologies can we deploy to predict and mitigate the risk of seismicity for geothermal projects? And what learnings can be transferred from the oil and gas industry to help prevent seismicity events as geothermal development grows? Let's explore.
Welcome everyone to Pivot 2021 and this panel on solid ground, induced seismicity forecasting, prevention and mitigation. I'm Katie Smythe from the Bureau of Economic Geology at UT Austin. I work with the Center for Integrated Seismicity Research, which along with the TexNet Seismic Observatory has the goal of better understanding induced earthquakes through collection of high quality data and fundamental and applied research. I'm honored to be moderating this discussion between industry and academic experts today. We're going to delve into a really timely and important topic of induced seismicity related to geothermal operations. Forecasting, preventing, and mitigating seismicity is arguably among one of the greatest challenges as we seek to safely scale up geothermal energy, particularly with new approaches such as enhanced or engineered geothermal systems. In recent years, we've seen projects put on hold or terminated as a result of felt seismicity, highlighting the importance of this topic, not only because of the risks of induced seismicity, but also because of the economic implications for the public and for operators. In this panel, we plan to cover topics including the importance of distinguishing between hazard and risk, what learnings we can take from oil and gas industry experience and apply to geothermal systems, and the role of high quality seismic monitoring and mitigating risk. The first thing I'd like to do is invite our panelists to introduce themselves and to share the perspective and expertise with which they're approaching this topic. So let's go ahead and start with David Haddad. David, will you introduce yourself?
Thank you, Katie. Good morning, good afternoon, and good evening, everyone. My name is David Haddad. I'm the president of the American Association of Petroleum Geologists, Petroleum Structure and Geomechanics Division. We represent academic leaders, business leaders, industry leaders in the space of all forms of subsurface hydrocarbon energy and also non-hydrocarbon energy as well. We've worked with operators and business leaders and academic leaders as well in terms of characterizing subsurface risk of induced seismicity and also its surface implications as well.
Fantastic, thanks, David. Let's move to Chris Panko.
Hello, I'm Christine Panko. I'm the Associate Director of the University of Utah Seismograph Stations. We monitor a seismic network throughout the state of Utah and in Yellowstone National Park. I'm also charged with monitoring seismicity at the Utah Forge Project. In addition to my seismic monitoring, I'm a research professor at the university in geophysics.
Thanks, Chris. Let's go ahead and move to Bill Ellsworth, please.
Yes, hello, this is Bill Ellsworth. I'm a professor of geophysics at Stanford University, where I also direct the Stanford Center for Induced and Triggered Seismicity. This is a group where we work with industry, primarily on issues within the petroleum industry, but we also have interests that extend into geothermal and other areas. As a researcher, I'm a seismologist. I study the mechanics of earthquakes, and that has been important for our ability to develop an understanding of the sources and consequences of induced seismicity, particularly for enhanced geothermal system projects.
Thanks, Bill. And Ola Kovan, please.
Hi, folks. My name is Ola Kovan. I'm a research geophysicist at the USGS Earthquake Science Center in Moffett Field, formerly Menlo Park. I spend most of my time worrying about seismicity at geothermal, EGS, and CO2 sequestration sites, and my research focuses on the monitoring of seismicity, assessing of the hazard, and the causes and effects of induced seismicity in those settings.
Fantastic. Many thanks to our panelists. I have a series of 4 topics that I'd like us to touch on right away. So in each case, I'll ask one of our panelists to give an introduction, a sort of state of the science on that topic, and we can hear from any other panelists who have additional thoughts. The first thing I'd like to touch on is how to talk about characterizing the risk of induced seismicity as we seek to scale up geothermal energy. I'll throw this first to Bill. Bill, we've seen different approaches taken by stakeholders and the media in characterizing the level of risk of induced seismicity. What's your view on how we can constructively frame the discussion around induced seismicity, hazard, and risk with geothermal development?
Yeah, this is really an important question. I think one needs to step back a little bit and think about where do earthquakes occur in the world. And the answer is primarily on plate boundaries, places like the San Andreas Fault System in California, but literally earthquakes can occur anywhere in the earth. And this is because stresses are high, particularly in the basement. So there is the potential for earthquakes almost anywhere. The question is, will a project disturb faults, which are optimally oriented in the current stress conditions that can lead to earthquakes that are of concern to society? So I think one has to begin with a basic geomechanical understanding of the system, of what the details about the project are, and then within that frame what the possibilities are. What is the potential for earthquakes of various sizes, and what might the effects of those earthquakes be, so that rational decisions can be made about how to proceed in a way which is both most effective from the standpoint of the project, but also safe in terms of protecting people and resources.
Excellent, thanks. We will come back to this discussion on hazard and risk in a few minutes, but I want to move on to a question for Ola, and that is talking about site characterization. So what are some of the important things to consider in terms of site characterization, and how might the local scale approach that's needed in geothermal differ from some of the basin-wide approaches taken in oil and gas?
Yeah, I think that's a really important and fruitful discussion, because geothermal resources in general, whether it's EGS or conventional, are generally much more confined to a small volume of interest. And that then in that case, the characterization of those sites can be much more detailed and much more realistic of what faults there are and what hazard they pose. And so many methods are generally employed in doing these site characterization, including potential fields, which have the ability to detect faults that are near or at the site, which is, of course, unlike what we've seen in wastewater disposal, for example, across the central and eastern US. And so with those detailed characterizations, the seismic hazard assessments that are generally done can go beyond stochastic methods, but can include deterministic geomechanical and very detailed models to really assess the hazard that is posed by any operation at a particular site. And geothermal in general, whether it's EGS or conventional, has generally welcomed the seismicity because it illuminates the pathways for heat and fluid that can be exploited. And so there's been a long effort in assessing the hazards, coming up with strategies to mitigate the risk, which most prominently, I think, has been featured in the best practices in geothermal development that was led by Lawrence Berkeley researchers, that consists of 7 specific steps that include identifying the hazards, communicating what hazards there are, and coming up with mitigation strategies. And so I think geothermal, despite its setbacks at a number of prominent locations, really has a potentially a better setting in which hazard can be assessed and the risk can be mitigated.
Fantastic, thanks. Chris, I've got a question for you, which is, can you talk a bit about the role of forecasting and mitigating seismic risk and what's required on the monitoring side to improve our ability to forecast?
So I think this is an important topic to get at some of these issues we've had in the past. I agree with Ole that, you know, in geothermal, it's a small area, so we could actually do really detailed monitoring. We can go in and look for the faults. We can do fault studies and such. But sort of understanding, going back to what Bill said, the earthquakes can kind of happen anywhere. How do we get at that stress state, and what do we look for? I think these are really fruitful areas of research right now in terms of forecasting and in terms of collecting the data, processing the data in real time, looking at relative event locations, looking at size of events, looking at the past seismicity and the current seismicity, but learning how to do that in real time with some type of forecasting capability. Not that we're going to predict what's going to happen, but can we get a sense of how the seismicity is moving and what it might portend.
Excellent, thanks, Chris. And then an introductory question for David. David, with your background in industry and your role at AAPG, I would love to hear your view on what are some of the learnings that we can take from induced seismicity in the hydrocarbon industry that might help us moving forward in geothermal.
Oh, that's a very good question, Katie. You know, in oil and gas, we've come a long way in terms of identifying induced seismicity risks and characterizing them, and working with regulators and government agencies and peer operators, and also academic professionals and professional societies to characterize the risks and develop mitigation strategies that minimize induced seismicity risk. From the oil and gas perspective, there are two primary drivers for that risk. The first one is the disposal of produced water via saltwater disposal wells. So there's been a broad and a deep line of literature that's been published on that aspect of induced seismicity. The other one, of course, is triggered seismicity, which is related to hydraulic fracturing. So again, the industry has gone through a lot of research and has funded a lot of research to help characterize those risks. And also, part of the characterization is monitoring. So one of the biggest success stories that I can share is the seismicity monitoring network that we've set up in Texas called TexNet. And we have several dozens of seismometers installed throughout the state to monitor seismicity, both natural and induced. That was a collaborative cooperation between oil and gas operators, surface landowners, the universities. Obviously, it's been run out of the University of Texas Bureau of Economic Geology, and also peer operators and academic institutes as well, where we all sat down at the same table and we said, look, we recognize there's this risk that exists. How can we find that happy medium where we can continue sustainably developing our oil and gas assets and resources while we manage the risk of induced seismicity? So we've come a long way since the early days. And I think that from the geothermal side of the coin, there's a lot of learnings that we can transfer over from oil and gas in terms of monitoring induced seismicity, characterizing the risk, and also developing mitigation plans to address that risk. And most importantly, I think we have to have an open dialogue between geothermal operators and also regulators. You know, we cannot exclude the regulators or the energy regulators from the discussion. Again, speaking from experience from the oil and gas world, that was a very key step that we had achieved, which is inviting the regulators to the table and working with the regulators on developing guidelines that make sense both from an operator's oil and gas perspective, but also from the public's perspective and from doing what's right. So that's one stakeholder that geothermal. The geothermal world really has to think about as well, is get the regulators involved early, education, awareness of the risks and the science behind it, and also how can we intelligently mitigate against those risks.
Mm-hmm. Thanks. Following up on that, I'm interested. So Ola, do you have any insight into recent examples, maybe in geothermal, where there have been successful dialogue between stakeholders, successful community outreach in geothermal systems?
Yeah, as I mentioned earlier, the best practices document that's generally been adhered by most developers and production companies outlines as part of one of the 7 steps, communication with stakeholders, community, and so on. And I think that a particular step in the mitigation plan was added by the authors of that, is because there's a very good history and long history of community involvement at the Geysers geothermal field. So there's clear communication about what is happening. There's a dedicated monitoring, seismic monitoring network that shows publicly all the results, and it's a very high fidelity network. I believe there's a community fund. If there is an earthquake within the reservoir and you have some minor structural or minor damage to your house, you can apply to have the cost of remediation of that paid for by this fund. So these steps of success stories are really important. I was part of another Forge proposal that eventually didn't get chosen. But we, for example, in the outreach effort, went to the local harvest festival in Fallon and explained what we're planning on doing. And in general, when you communicate openly what you're doing, what the associated hazard and risks are, the community is much more prone to be supportive of what you're doing. And I think that's an important component where, you know, the geothermal energy community has been at the forefront of doing that kind of engagement for a long time. And it's been very successful.
Excellent, thanks. Staying on this topic of hazard and risk, Bill, I'd like to come back to you. Do you have recent examples where you think maybe there were appropriate responses to risk versus examples where stakeholders might have responded to hazard, or differentiate a bit for us on that, please?
Yeah, no, that's a really very good question. As some people may know that there has been a relatively new enhanced geothermal system project in France. This is in eastern France in Alsace, just north of the city of Strasbourg. And they've had a number of problems with induced seismicity. Most recently, the wells were shut down about 6 months ago, and only a month ago they had an earthquake that was widely felt. So they realized they have issues there. But the information is very public. It's very straightforward what they're doing. And this has, I think, been a success story in terms of the importance of communication, keeping the public well informed. Perhaps a project that didn't perform quite as well in that direction would be the project that was attempted in Korea a few years ago. And this is where a damaging earthquake was induced by the project, triggered as it was. And here, I think there was a lack of transparency, a lack of communication, which really complicated the situation as it unfolded. One thing that I think we've learned from the more successful projects is the importance of public information. As Ola was saying, if we look at the geysers geothermal system in California, this huge natural system, having information that is freely available and easy to access has been very important for all stakeholders. And I think that's a lesson that would be wise to be absorbed by anyone contemplating a new project.
Excellent, thanks for that insight. You mentioned Strasbourg there, and I wanted to revisit that briefly. David, with your background in geomechanics and integration, can you talk a bit about the mechanism for that type of seismicity many months after a project or a well is shut in? What does that look like in terms of causality?
It's very hard to link causation of these events, seismic events, to operations. You know, this is the holy grail of induced seismicity, is being able to make that link. It's very basin specific. It's very operations specific. It's very rock specific and reservoir or aquifer specific. So whatever tie we can come up with for that event may not be applicable to other events or other clusters or sequences of events in other basins. It depends on how critically stressed those faults were before injection, and their critical stress evolution during injection, any type of poroelastic relaxation after injection. You can run the gamut of phenomena, of natural phenomena that could be responding to the injection. So there's no one silver bullet answer to it. And this again goes back to the emphasis that if we were to really think about induced seismicity and characterize it holistically, we have to be flexible enough to start thinking about local site characterization, local fault characterization, and local operational parameters characterization, and how all three of them interplay with each other. So again, there's no one right answer to those events. Generally speaking, when you have events that occur months after operations, injection operations, geomechanically, again, in theory, it tells you that there's some type of pressure transfer from where the injection took place to where that critically stressed fault is located in three-dimensional space that tipped it over the edge and had it break and cause earthquakes. The exact mechanisms, and we can delve into the details there, but again, it goes back to my point in terms of that specific mechanism, if it's true, may be specific only to that fault or only to those events. Again, I'd hate using generalities and broad brush statements to say, yep, that's the event, that mechanism is observed or is applied to everywhere else, to other events too. Again, it just emphasizes the need to think about these basins as individual basins with their own characteristics. Same thing with our operations. It depends on how you operate those wells.
Thanks. Do any of our other panelists want to jump in on that topic?
Yeah, I would like to. Actually, David is absolutely right that the specific cases and specific sites are all have their complications with it. The, of course, added complication in geothermal settings is that thermoelastic stresses play a very important role, especially early on in the production regime. So the causation or the assignment of causation is even more complicated than it is in oil and gas applications, where generally low pressure diffusion or elastic effects allow you to make some sort of statement on what the causation was. That is more complicated even in geothermal, so it becomes even more complicated. And I totally agree with David that the site-specific conditions can vary vastly, even within the basin and range, for example. So it's very difficult and requires a local assessments, characterization, and monitoring and modeling.
Thanks. I hear you all hesitating to make any broad generalizations, which I appreciate. But I would love to see if we can distill what do we know and what have we learned about induced seismicity in geothermal systems. Are there any learnings that can be broadly applied? So I'm thinking past experience like Basel and more recent events, Korea, France. Are there things that these events have in common that can be generalized across them? And I'm happy for anyone to jump in on that.
Well, maybe I could jump in and say a couple of things. And I'm glad you mentioned Basel, that being one of the important early cases. And I think it really demonstrated the value of having very detailed monitoring so that there was a good understanding about the seismicity as it was occurring that allowed also for an understanding as time has developed. Basel's an interesting case in part because of the trailing seismicity. David was discussing that in the case of Strasbourg. In Basel, the largest earthquakes occurred after shut-in, and some of the large ones occurred months after shut-in. It's quite interesting there that they have had to bleed those wells recently because pressure was building up. And I think that gets back to Ola's point that these are very complicated systems, that there is going to be natural pressures that will be evolving due to the perturbations that are made in the creation of the system. So all of these things need to be studied and monitored in perhaps much greater detail than we're used to thinking about in terms of many other drilling adventures that we undertake. Having information that's collected within the formation, pressure and stress data, seismicity that's precise are among the keys that are needed to really understand how the system is performing and where it's headed.
Thanks. Bill, since you mentioned monitoring, I would like to go in and I'll bring in an audience question we've already received and send a question to Chris. What do we know about natural seismicity in some of these regions versus induced seismicity? And the question that came from the audience is, many geothermal resources are associated with seismically active magmatic centers, such as Brawley seismic zone. So how do you distinguish between natural and induced seismicity and effectively communicate this distinction to the public?
So that is a good point, right? So we typically have geothermal where we have active tectonics. So coming back to the best practices that Ola's been mentioning, is one thing is to characterize the seismicity before you start anything at a geothermal site, so you can get a sense of where what I'll call natural seismicity is occurring versus what might later be induced, although that can get complicated as well. Typically, if I look at the Forge example, Forge is sort of a unique place in that we really don't have a lot of background seismicity. We've been monitoring there since 1981, have a really detailed catalog. I can tell you that most of the natural seismicity occurs in the mineral mountains, and we don't really record seismicity out in the basin. So if we see events out in the basin, I can point at it and say, that's an unusual event. We can look at it in terms of what happened at Forge to try and assign whether it was induced or not. But just based on the history, and I think you can do that in a lot of places, because in natural seismicity throughout Utah and even up in Yellowstone, it's dispersed in some sense, but there's pockets of seismicity when you start to dig in. You start to see where some of these seismically active zones are. So you can't uniquely separate them, but I think there's ways, as long as you start before, so you have clear before and after, I think is the best practice.
Excellent, thanks. I'd like to follow up on one thing there. So do you have thoughts or advice on how we can design experiments or investigations to give us the information we need to accurately monitor and catalog events? What types of data are needed? I think your experience can speak to that.
I actually think that's one of the exciting things about Forge, is that in a sense we're experimenting with that. We're trying to take what we know from other industries and what has been done in geothermal. So for the first stimulation, we'll have 3 deep boreholes down at reservoir level that will be monitored with industry geophone strings. We've got 2 DAS cables. I think I heard today the second one was just cemented in or will be cemented in this week. So we have DAS, we have the geophone strings. When the stimulation's over, we'll reoccupy those holes with high temperature strings to sort of look for post-stimulation events. We'll see it's tricky in geothermal, it's really hot. So finding sensors and cable and gaskets that are going to survive these temperatures is a non-trivial exercise. So we'll see how long we can keep these sensors operational. So that's kind of at the reservoir level. In addition, we have a surface network and shallow borehole network. So we've put in a number of what in the earthquake seismology world we call post holes. So these are sort of deep post holes going down to 100, 150 feet. And as well as surface stations on rock to sort of capture any larger events or events that might migrate away from the Forge site. We have surface geophones. So we have a pool of instruments that we can go out with for temporary deployments. And we've been experimenting with all different types of array deployments to see what gives us the best detection and location capabilities, hopefully getting at some source capabilities. So can I give you the one answer today? No, I can say that putting the deep boreholes in from some of the previous tests, we get better detection and we get better location. We only had 1 before. With 3, we should expect something better. But I think that's one of the exciting things about Forge is we have all of these different data sets. We can do the experimenting. We co-locate sensors down holes to see what's better, which one behaves better. So yes and no. How's that?
That's great. That's perfect. So one of the audience questions that's come in is says that we keep talking about EGS, which we have done a lot of, but what about induced seismicity associated with conventional geothermal operations? And I'll open that up to all of you, if anyone can speak to induced seismicity in conventional geothermal.
I guess I'll take it. I'll take that question. So it gets back to some of the earlier questions of how do you decipher between what was there before and what do you now induce by the operations. And for the example, specifically in the US of southwestern California, Northern California at the Geysers and Basin and Range, all of these areas are high strain rate locales that have seismicity associated with them in the first place. And so it is very, very difficult to distinguish between what's natural, what is induced. It probably doesn't matter all that much just because you do have earthquakes in these locations that might be accelerated, or their occurrence might be accelerated. The one, I guess, positive takeaway from that is, especially for the Southern California and Northern California fields, is that the brittle ductile transition, of course, is very, very shallow in these regions because there is high heat flow. So there is a limit to the magnitudes that can be generated in many of these Western US geothermal areas. And of course, that general region is used to earthquakes of specific sizes. And so Yes, there have been significant earthquakes in geothermal fields. The geysers gets routinely earthquakes in the high 4s. COSO gets earthquakes in sort of the low to mid 4s, not very frequently. The Nevada sites obviously have quite the potential for large earthquakes as well, just judging by some of the historical events that are pretty close to active geothermal areas, but I'm not aware of any large events within any of the Nevada conventional geothermal sites.
Mhm. Excellent, thanks. We've had a question come in, which is something I'd like to talk about, and I'll send it first to David for oil and gas perspective and then to Bill, if that's okay. And the question was, what percentage of induced seismicity in the oil and gas world is caused by fracking and not by wastewater injection? And then how is this similar or different in a geothermal context? So David first.
Sure, I can answer the first part. It's difficult to separate the two, again, because the characteristics of the seismicity that's detected from both sources are about the same. So it's difficult to separate the two without looking specifically at timing and the periods when wells were being stimulated and trying to spatiotemporally correlate those two events to seismic events. But generally speaking, with wastewater disposal, there's a long, those wells inject over long periods of time. And so the seismicity tends to be a bit more clustered along faults that are near those injection wells. And it seems to be, they tend to be more sustained in terms of the duration of the seismicity. Whereas with hydraulic fracturing, if there were any induced seismicity on nearby critically stressed faults, then those events would be more pronounced in time and they would be short-lived. But again, there's no golden sort of rule to use to try to separate the two, because characteristically they look about the same. There are some methods that the oil and gas industries has worked with earthquake seismologists to try to tell the difference between the two. And if you look at sort of earthquake seismology 101, where you look at the Gutenberg-Richter distribution, magnitude distribution, frequency of earthquakes, that can then start to tell you something about the causation of those events. However, in order for you to have that level of resolution, you have to have industry-grade seismic monitoring stations directly above the source fault that caused those earthquakes, whether it's directly above your hydraulic fracturing operations, or it's directly above or near your saltwater disposal well, or any critically stressed faults. So in order, that's again, it goes back to there's no real one silver bullet for answering that question. It really depends on this from site to site, from operation to operation, and from the stress state of that fault to other faults.
Thanks. Bill, I'd love to hear from you on this.
Yeah, just to add a little bit to what David said about the operations within the industry, I think it's also worth mentioning that we've seen much larger earthquakes that we can associate with wastewater disposal than we can with hydraulic fracturing. There have been some very serious earthquakes that have been associated with fracking in China, but fortunately we haven't had that experience, at least to this point in North America. And I think most seismologists who've looked at the question would probably attribute something like maybe 90% of the earthquakes in Oklahoma, and we're beginning to think similarly in West Texas to the saltwater disposal issue rather than fracking. So how does this play into enhanced geothermal systems? It really comes down as to when are the industrial activities that are changing the stresses occurring. We know that in development of unconventionals, the risk in fracking is primarily when you have the pumps on. It can continue after the pumps are off for a relatively short period of time, but the seismicity typically fades away. What we've seen in geothermal, at least in some of the projects that have been problematic, we've mentioned Basel, we've mentioned Strasbourg, we've mentioned Korea. There it was seismicity that lingered for months or even longer afterwards. And we don't really have a very clear understanding at this point. In part is, I think, because of a lack of really good geophysical control. And of course, this is one of the important things that we hope to learn from projects like Forge, where we have much better control about what is happening on the subsurface. And then we can use that to inform possible mechanisms that might be anticipated. But I think for now, I think most of us feel that at least simple models can be used to assess the risk. That probabilistic models that track the trailing seismicity are useful both in the fracking context as well as in, I think they will also be useful in the geothermal context as well.
Excellent, thanks. I'd like to follow up on something you touched on. And we talk a lot about operational decision-making in creating risk for induced seismicity. I'd be interested to hear, and I'll throw this to Ola first, are there any cases in which we could creatively harness operations to reduce risk, specifically in areas that do have native seismicity? So I'm thinking about the idea of thermal de-stressing as a proposed mechanism at COSO. So I'd love to hear your thoughts on that.
Yeah, I think you're referring to a recent Nature paper that suggested that the ongoing geothermal exploration at the coastal geothermal field led to a decrease in total seismicity rate following the Ridgecrest earthquake when compared to surrounding areas. It's a compelling hypothesis. The authors postulate that the reservoir, since its inception in the 80s or so, has decreased in temperature by about 100 degrees C. Unfortunately, the authors do not have access to any of the reservoir data that might support that. And so since there is no data that could verify whether there's a 100 degrees C drop in temperature, which I think is on the very, very, very high end, I just don't think we can really make that argument that thermal de-stressing is taking place. Many of the conventional geothermal resources in the Western US have really long-lasting, very high temperature heat sources beneath them, and probably have enough temperature in the rock for much longer than many of the sort of 30-year life cycles of envisioned for more basin and range type of geothermal fields. So I personally don't necessarily buy the argument of thermal de-stressing and decreasing the seismic risk. However, what is seen in many geothermal operations, what has been used for decades, is if production wells are changed to injection wells and temperatures change, there is an uptick in seismicity near the wellbores that are being changed from high temperature to low temperature type of environments. And so that certainly takes place, and that's a very local phenomenon that's not very long-lived. I know similar things are observed in oil and gas operations when wells are shut in or workovers are taking place, that seismicity at times increases. But I don't think there is a long-term trend, and it's certainly not a tool for seismic risk reduction, and most definitely not along the Senator as well.
Thanks for that. Bill, do you have any thoughts to add to that?
Yeah, let me add some of the experience we had with the project in Korea that we were talking about. This was an attempt to develop a small electrical generation facility outside of the city of Pohang, which is a city of about 1 million people on the east coast of Korea. And during the course of the project, they had 2 wells. And when they injected into one well, they kind of got the puffy cloud of seismicity that one would like to see, that would indicate that they were creating a connected volume in which they would be able to pass fluid as a heat exchanger. In the other well, they never recorded seismicity near the open hole section that they were pressurizing. Instead, what they did was they began to activate a fault. And they didn't know that they were activating a fault. Perhaps if they had seen that, they would have realized that they were getting into very risky territory. What eventually happened there was that an earthquake got nucleated within that activated zone and expanded out of it. It expanded far beyond the region that was perturbed, producing a very serious earthquake that caused about $1 billion worth of losses of direct and indirect economic loss in Korea. So a very serious situation. So I think this comes back to one of the points that Ola was making, that it's really important to have a full understanding about what the system is doing, both during stimulation and during production, so that these competing hypotheses can really be nailed down in terms of the science.
Go ahead, Chris.
I just was going to chime in. There was also the experiment in Finland where they were drilling a deep geothermal well and injecting, and they had really good monitoring going at the time. And they also had a really strict constraint from their regulators. So the whole project would shut down if they got larger than 2. So as they monitored this with their network, they were able to adjust. I can't remember if it was pressure or rate or volume or rate, but just in the monitoring process, this change what the production was doing actually seemed to have an influence directly on the seismicity, or at least according to the papers that I've read.
Excellent. That's really interesting. And I do want to get to a discussion on traffic light systems and in a few minutes, but sticking with what you're talking about in operational decision making, what does the panel think about the idea that maximum earthquake magnitude is constrained by or is a function of the volume of fluid injected? And Chris, I'll stick with you first on this if you have anything to say, and David, maybe you can speak from oil and gas industry experience.
I personally think if you look at some of the initial work, there's a strong correlation. There's always the exceptions though, and I think it depends on who you talk to. I think there's multiple ways to get at the maximum magnitude. So I think the volume's one way to look at it. I think you can look at sort of going back to Gutenberg-Richter type relations and such. So maybe looking at this problem from more than one direction might be the better way to go. But if you just look at some of the initial plots, I know that Pohang plots off the initial plot and some other events plot off that volume relation, but a large number of events plot very close to that relation as well. So it might be a good help guide things. I don't think it might get to the maximum because I think ultimately your maximum magnitude is going to relate to your background. So what is your largest fault, which I think might be what we saw in Pohang, just my personal opinion, that there was a larger fault structure that was activated. So I think you have to look at this a little bit more holistically in terms of what is the background, what is the volume and rate. There's correlations with rate as well. And then also, what can you say about the seismicity and sort of look at it more holistically.
Excellent, thanks. David, do you want to jump in on any learnings from oil and gas on this?
Yeah, let's step back even like before oil and gas. Let's just kind of remind ourselves, if we're thinking about moment magnitude, so what goes into that calculation? It's a couple of things, three main variables. First one is the strength of the fault. The second one is the area of the fault that slipped, that broke. And the third one is the amount of displacement that happened on that fault during that event. So as you can see, there's no direct mathematical relationship to injection volumes or injection rates. So there's a physical disconnect between what's happening at that fault during the earthquake and what's happening operationally. The connection between the two is whether it's poroelastic stresses being transferred between the injecting wells and the fault, or if it's thermoelastic from the geothermal standpoint. So making that connection, that's kind of the missing link that I think the focus of studies and research should be on. Again, it goes back to how critically stressed those faults are, and that's a function of where those faults are in their earthquake life cycle. It depends, again, if you're talking in an active tectonic setting and they're going through their usual earthquake life cycle. If you're talking through about dormant faults that haven't slipped in the last several million years or the last major tectonic event, then those faults may be brought back to life with injection. Again, there's a physical link that is missing between the maximum possible earthquakes that are generated, or not maximum possible, but the earthquake magnitudes that are generated versus what we're doing operationally. With that said, there are some things that the oil and gas industry, again, having worked very, very closely with academic research institutes, including Stanford SCITS and the UT Austin BEG scissor program, working with regulators as well to develop ways to think about what can we do operationally to reduce the likelihood of us causing large events during saltwater injection or during hydraulic fracturing. And those things rely very heavily on constant high resolution monitoring of seismic events during operations. If we see the frequency of events increasing or the magnitudes of events increasing, then maybe one operational parameter to change is to reduce the injection rate or to slow down your completion, your well stimulation operations, the rates of those. It's entirely dependent on the basin that you're operating in, on how close you are to those faults, if they're critically stressed. Of course, what the regulator says too. In some states or provinces, regulators require constant monitoring, seismic monitoring during hydraulic fracturing operations to account for that and monitor the seismicity increases or decreases. Some states don't. So it's a function not only of the subsurface and what's happening between the wells and the faults, but also with what's out there at the surface in terms of providing guidelines for the operators and building some of those sideboards that operators need to think about when they inject.
Thanks. Chris, is there anything you want to follow up on there before I move on? You can say no.
No, I mean, I'm kind of an empirically based person. So, so when I look at, you know, the volume and maximum magnitude, there's a clear correlation there. So can I describe the physics of what's going on? Not necessarily, but especially in a place if there's been no seismicity and you start injecting and you put that volume in, there's tends to be some type of correlation, causation we can argue about. So I think, my apologies, my dog's in the background. I think we need to sort of pay attention to what's happened in some of these areas and include that evidence.
Thanks, that's helpful. Okay, I'm going to lump together several questions on a theme from the audience that I'm hoping we can address through a couple of you. One theme is about sedimentary development versus basement formation development and whether we might have lower seismicity risk in sedimentary basin development as opposed to basement. And then another question is whether we need more accurate fault and fracture mapping. So specifically, this idea of geothermal anywhere, does that require a comprehensive basement fault map anywhere to avoid injection for EGS in the vicinity of a favorably oriented fault? So I'll go to you first, Ole, on those two, if you want to speak, since we're talking about faults in sedimentary basins and basement and fault and fracture mapping. Thanks.
Yeah, certainly. I think what uncertainty or what hazard one runs into that is similar to the seismicity crisis across the central and eastern US, where basement faults are activated that are with their locations and extents and how they're stressed being unknown. So that might be a scenario similar to that for geothermal development in sedimentary basins. Again, in sort of basement or near surface outcrop basement development or volcanic type region development, the fact that the resource is very near surface and a number of methods can be brought to bear to characterize the site would probably benefit the risk and hazard analysis prior to exploration. How exactly that would look in a basement and in which basement, it's unclear to me. Of course, Katie, you and I talked that the Western Texas basin may have faults within the basin, within the sedimentary horizons themselves that might be part of what's causing seismicity there. So again, there might be a number of complications there. I think our experience, of course, is mostly in these sort of volcanic and near surface types of outcrops. So we certainly would have to lean on what we've learned from central and eastern US seismicity in sedimentary basins if development of geothermal in those types of regions were to take place. And I think the uncertainty would go up. And again, it would go from a local scale to a much broader scale. So it complicate the hazard assessments, in my opinion.
Excellent, thanks. Would any of our other panelists like to jump in on that sedimentary versus basement?
Yeah, let me add just a couple of thoughts here. One thing I think to keep in mind is that we have a lot of experience of cycling fluids within sedimentary reservoirs. So for example, EOR depends pushing water or other fluids through to extract oil. So it's not going to be that different than perhaps the production of heat as well, extraction of heat. One lesson we've learned, I think, from EOR is that you do sometimes get seismicity, but not often. And I think the other key point to make about the sedimentary section is whether there is the potential of intersecting faults that are critically stressed in the contemporary stress field. I think that would be kind of the real point at which you would begin to be concerned about a hazard. So those would be things that would be important to be keeping an eye on during the development of a field. With regard to basement, things are much dicier there, in part because almost all of the permeability is the permeability you're going to create during the development of the project, unless you're dealing with a natural system. And because it's very difficult to identify faults using geophysical methods in basement, one simply has to be extremely tuned to the possibility that seismicity will be lighting up structures. As David was pointing out, to get a big earthquake, you need to have a large fault area. So when you begin to see structures that look like they're extensive, those would be the times to get concerned, because then you might have the potential of one of these earthquakes that runs away from the stimulated zone, tapping into the natural tectonic stresses and producing a large earthquake. I think it's also worth mentioning that, you know, one of the promising areas of development for geothermal, particularly in Europe, is to not develop geothermal energy for heat and for electricity, but for direct use for heating. And that has a lot of promise as well. You could be working in karstic terrains so that there's going to be there's going to be high permeability, natural permeability, and the risks would be much lower in those kind of situations. Of course, then monitoring is going to be important as well, just to make sure that nothing unusual begins to happen, so that you're aware of any changes in the system that production brings about.
Mm-hmm. Excellent, thanks. We have a lot of audience questions, and I'll try to group them for the next bit of time we have left. One is about closed loop systems. So we've been talking a lot about EGS, and Bill, you mentioned direct use. I'm wondering, and the audience is wondering, whether closed loop systems would have lower induced seismicity risk. Are there any thoughts from the panel on this, whether those claims might be true? No one knows. Might be back to you, Bill.
Well, it's an interesting question. I mean, the difference between closed loop and open loop might just simply be the fluids that you're circulating. You're going to be moving heat around, so you're going to be creating thermal stresses, as Ola was pointing out, and so I think that will be a concern. I think to date, most of the issues have been related to actual development of the system rather than the production. Mm-hmm. Production in the geysers, for example, as Ola was pointing out, has led to kind of larger and larger earthquakes over time. But the earthquakes have been very important in terms of the maintenance of the field. So how a closed loop system will work out is kind of a very interesting open question.
Mm-hmm. Fantastic, thanks. We've had a lot of questions about standards, traffic light systems, mitigation strategies, things on that topic. So I'd like to spend a little bit of time addressing some of those. We'll get to as many as we can. Traffic light systems have been proposed and variably implemented in different operational environments. So I'm wondering if anyone can speak to examples of successful mitigation strategies where there's been a traffic light system that was successful in mitigating seismicity. So Chris, maybe do you have thoughts on that?
I think I'd go back to that example from Finland. I think, you know, they had their traffic light system. They saw the seismicity changing. It had a direct relation back to the operations. They changed the operations. They continued to monitor, and they saw changes in what they were recording. So I think that's a positive part of the traffic light system. I think in some ways they're tricky, right? Because at magnitude 2, that's a pretty small earthquake, and you'll be lucky if you feel it at the surface. But so you're trying to set the traffic light system to have, if you use magnitudes that are low enough that you can stop, or you can change the seismicity before it gets larger. So you have this really low value versus, or you could say the same with ground motion. So I think there's work being done in terms of adaptive traffic light systems. And I know they partially implemented that in Finland. So where you look at rates and such. So I think there's more room for a traffic light system. I think it's a positive though, because you're actively paying attention to what's happening, and you've set up that, like we talked about communication before in terms of communication with the public, but now you're communicating between the people monitoring the seismic or the seismicity and the people operating the well, and you've set something up ahead of time so that you have clear communication there. So I think in some ways that's going to be how we go with whether we have a standard traffic light system or adaptive traffic light system, but having that communication so we don't get these larger events that raise some concerns, I think is a really important direction.
Thanks. David, I'd like to hear from you briefly on what are your thoughts on how operators and regulators can work together from your experience to decrease risk, whether it's through one of these type of traffic light systems or other types of communication.
Yeah, so the example, a success example I can use is the one we have in Texas that was recently implemented a few years ago. And again, I keep harping on this point, but again, it goes back to the importance of open communication between operators, be it oil and gas or geothermal operators, regulators, public policy, and the public in general, and to build our understanding of what risks are there and what are the likelihood of those events, large events occurring, and how can we mitigate against those. So in the Texas specific example, we worked with the Texas Railroad Commission, which is our oil and gas regulator here in Texas, and other oil and gas operators and saltwater disposal companies, where we all sat down together at the same table and we looked at what are some of the seismicity throughout the state looks like. And that was really kind of the big push for us to work with University of Texas to start deploying the seismometers that we have throughout the state. So step number one is figure out where is the seismicity, be it natural or non-natural. Identify where the seismicity is located. Step number two is figure out where are the faults that are responsible for that seismicity. You're not going to have seismicity like that if you don't have faults available to release that co-seismic stress. So that's step number two. And step number three is figure out what is the optimal distance that my injection wells can be from those faults where we feel comfortable we will not generate earthquakes of concern or earthquakes of significant size. And then from there, work together on putting together a stoplight system that is more on the response side of the events, whether you have small events that fall under the green stoplight system, in which case the operator is not required to report those events to the regulator, where that progresses up to the orange part of the stoplight system, where it's proceed with caution, monitor the seismicity, and if it's red, pick up the phone, call a regulator, look at what happened, do a look back analysis, and see what may have caused those events. That was a pretty, I mean, I called it a success story because it was really getting together folks from the two primary industries that are associated with seismicity here in Texas, but also sitting down with the environmental regulators, oil and gas regulators as well, and having an open dialogue. And so with that, with the steps that were developed were fairly systematic. Guidelines are fairly clear. Everyone understands what data are required to be submitted in order for an operator to receive an injection permit, for example. What are some of the thresholds that are needed in order to be granted an injection permit of several tens of thousands of barrels of injection water injected per day versus say 50 or 60. So that it becomes a gradational system where it's not so black and white. And again, that's focused more on the basins. You know, in Texas, we have several oil and gas basins where we have oil and gas operations, and we also have saltwater injection. And again, going back and harping on that point again, every basin is different. Every fault is different. So we don't want to create a set of regulations and guidelines that are very black and white. There needs to be some flexibility built into them to allow the operators to do what they need to do while remaining within the regulatory guidelines and framework.
Mm-hmm. Okay, thanks. I'd like to follow up on this a bit, stay on this theme first to Ola and then to Bill. What types of data, methodologies, technologies we might need to improve our ability to mitigate seismicity? These might be things that could be incorporated into an adaptive traffic light system or maybe not, but what are the unknowns that we need to get a handle on?
Yeah, I think before any of that, an important part of the site characterization is understanding the stress state, because especially in these conventional settings, it can be highly heterogeneous, different from sort of the general surroundings. And so that's an important part. On the monitoring side, of course, having the more the merrier, really. I mean, the deep monitoring like it's done at Forge, it's amazing because you can sort of see changes in rates of seismicity. You can see the cloud evolve and maybe start to show up on structures you weren't aware of before. So I think the seismic data still is the one set of data that informs where faults are, how they behave, and what seismicity they might be capable of. So really deep monitoring at these sites, I think, is crucial. Obviously, the capabilities for that exist. The technological challenges to the temperatures and in pretty aggressive brine chemistry is obviously a challenge, but I think a challenge that can be overcome. The advances in fiber optic derived methods, whether it's strain, whether it's acoustics, or whether it's temperature, I think are extremely important. Seeing thermal breakthrough often is a much better indicator of where major faults are that can take a lot of fluids and might connect to larger faults is really important. And those things seem to be maybe more adept at being in geothermal holes because their temperature may be somewhat more temperature resistant. But I'm really excited to see what the Forge project yields with that because all of those technologies are tested. So I think downhole monitoring of anything and everything is crucial because every site can be very, very different, and every site requires very dedicated monitoring and sort of understanding on the fly, really, because your structural model that you have prior to injection may not line up with what you see once you start injecting itself. So I think being flexible with that and having dedicated and deep borehole monitoring is crucial.
Katie, I'd like to step back a bit, actually, to talk about hazard and risk, because most of what we've been talking about just now is the hazard that an earthquake might create. That's the shaking of the ground. But really what we're missing is the connection between that and the risk. The risk is a question of what's being exposed to the shaking and how fragile is it. So that's the thing that people are worried about. It may be that they're concerned about the nuisance of feeling earthquakes, or it may be they're concerned about physical damage. These are things that we can quantify and estimate before a project to understand what are the potential risks, and from that basis we can then begin to design systems that will say this is a risk that we're willing to accept as a project goes forward, or this is a place in which we've crossed the red line and we need to either adjust what we're doing or perhaps even stop. I think they're very, very good examples around the world from how these type of systems have been deployed. For example, in the state of Ohio has had very successful application of traffic light systems to manage fracking projects there. They've stopped some projects midstream, figured out what to do, and then gone back and successfully completed them. In other cases, the red lights have come on and it's been necessary to stop projects altogether. But I think it's this connection between who's going to be exposed to a project, what the factors are going to be that might create problems downstream that have to be assessed, and that's important to do it at the beginning. Forge, for example, is fortunately in a fairly lightly populated part of Utah, and the assessment there is it's unlikely anything will happen. But a project that would be closer to populated areas, we've mentioned a couple in cities, those are ones that really take a very careful approach. One that we've probably been short on developing at this point, but I think that's a really important frontier area that we have to explore. It'll go hand in hand with our development of a better understanding of the science about how the earthquakes are being generated and what we might be able to control the hazard. But we have to consider the risk side of the equation as well.
Yeah, excellent. Thanks, Bill. I'm going to stick with you for one final audience question, and then I'll ask us for some wrap-up thoughts from each of you. One of the questions says, there's no certainty with predicting induced seismicity. or not even with future technology, what are your thoughts for how to confront risk from a monetary and community insurance perspective?
Boy, that's a really good question. And it really comes down to the question of what is our risk tolerance? I think we have to ask the question that what are the cost benefits of a project? If there's a 1% chance of a project causing $1 million worth of damage, will we have insurance for it? If it's a 1% chance of $1 billion loss, how will that be covered? So I think it's really confronting those issues head on. And this is why I was saying earlier that we have to look at the hazards and do the best job we can in terms of quantifying their probabilities, but then we have to fold it in to look at what the risk is so that we have an assessment as to what the project may be exposing us to and who is willing to accept those possibilities.
Great, thanks, Bill. Okay, we're nearing the end of our time for this panel. I'd like to hear from each of our panelists briefly, specifically on your top recommendation or recommendations for how to think about safely scaling up geothermal while mitigating the risks of induced seismicity. So I'll go first to Chris on that one. Just a few final closing thoughts. Top recommendations for scaling up safely while mitigating risks of seismicity.
I think I'll just follow up to what we've talked about. It's a multi-step issue. Ole brought up the best practices that have been adopted by geothermal. I think that's a good starting place. I don't know that all practices are needed everywhere, but I think that's a great starting point because that gets to seismicity, that gets to looking at hazard and risk, that gets to monitoring, that gets to communication. And I think it's going to take all of those issues to move forward.
Thanks, Chris. David, let's hear from you. Final thoughts.
Sure, I have three main points. First one is seismicity of concern occurs on faults. So step number one, know where your faults are. Second point is monitor for seismicity during operations. Look at historic seismicity, monitor present seismicity, compare and contrast. And the third recommendation is have an open dialogue with all of your stakeholders, with your regulatory bodies, with your environmental bodies, local operators nearby, and develop a framework that's flexible enough for you to move forward with an upscale geothermal while reducing the risk of seismicity.
Thanks. Bill, over to you.
Yeah, just to add to that, I think transparency is such an important issue, both during the development stages of a project as it's being planned, so that all stakeholders are well informed about what is happening, what might happen. Certainly during the execution of the very active stages of the project when the reservoir is being developed, but also during operations. And making data publicly available, I think, is one of the key steps that is really important to engaging all of the stakeholders so that they have an understanding about the project's status and evolution.
Thanks, Bill. And Ola, to you.
Well, I'm going to sound very repetitive here, but I think first and foremost, site characterization is crucial. It's much more approachable because it's generally a smaller footprint. The probabilistic seismic hazard assessment can be done going farther than maybe what's done with just stochastic models. I think geomechanical deterministic models can play an important role. And lastly, and I think to me most importantly, stakeholder engagement is crucial at every stage of the project and really dictates the success of any of these.
Thank you for that. That's a great end to a very fruitful discussion. I'd like to thank all of our panelists for your time and the audience for your engaged and insightful questions. I hope that this will serve to spark thought and discussion, and we can continue this conversation about induced seismicity and geothermal projects going forward. Many thanks, everyone.
Thank you.